Welcome to Jotunheim, popularly known as the land of the gentle giants. King Laufey is the kind and fair leader of these humongous creatures, but his two sons, Paulo and Rio, are not so level-headed. Every year, when their birthday approaches, the giants of Jotunheim begin to worry. You see, each twin receives a giant-sized gift from their father. But even if one gift is slightly larger than the other, both brothers start quarreling. Their bellowing blows the leaves off the trees, and their stomping sends avalanches rumbling down the mountains. The only way Laufey can keep the twins calm is by ensuring that their gifts are of exactly the same size. This year, Laufey is particularly anxious because Paulo and Rio have asked for completely different things. Paulo wants a mystery board game, whereas Rio wants a bronze shield. When these gifts are first bought, Laufey has no idea whether they're the same size or not. All he knows is that both gifts are shaped like a parallelogram, and that the lengths of their respective bases are equal. In fact, if both gifts are placed on top of each other, such that their base lengths coincide, then it can be said that the two parallelograms lie between the same parallels. So, if letters EFCD represent the vertices of the board game, and letters ABCD represent the vertices of the bronze shield, such that both shapes stand on a common base, CD, and lie between the same parallels, EB and CD. Can King Laufey determine whether the area of parallelogram EFCD is equal to the area of parallelogram ABCD? If so, prove how. The first thing we notice in our diagram is that the region denoted by letters A, F, C, and D is common to both the given parallelograms. In other words, we can say that triangle ADE is the only region which belongs exclusively to parallelogram EFCD, and triangle BCF is the only region which belongs exclusively to parallelogram ABCD. This means that all we need to do now is compare the areas of triangle ADE and triangle BCF. If these triangles are equal in area, then EFCD will also have the same area as ABCD. So, what's the best way to establish this? Well, based on our previous knowledge, we must try to prove the two triangles congruent. Let's start by exploring all the given details. We know that both ABCD and EFCD are parallelograms. This implies that line segment AD is equal to BC, and line segment ED is equal to FC. This is because opposite sides of a parallelogram are equal to each other. Based on this, we can conclude that triangle ADE and BCF have two pairs of equal sides. This gives us two options to prove them congruent. The first one is to use the side, angle, side criteria, whereby we'll have to show angle ADE equal to BCF, whereas the second method employs the angle, angle, side criteria, whereby we'll have to show angle DEA equal to CFB, and angle DAE equal to CBF. In order to pursue either of these methods, we must first focus on parallelograms EFCD and ABCD. Here, we see that the line segment ED is parallel to FC, and line segment AD is parallel to BC. This is because opposite sides of a parallelogram are parallel to each other. With these results to show for, we can conclude that angle DEA is equal to angle CFB. This is because Whenever two parallel lines like ED and FC are cut by a transversal like EB, each pair of corresponding angles are equal. Similarly, angle DAE is equal to angle CBF. Here again, we get a pair of corresponding angles because transversal EB cuts across parallel lines AD and BC. Knowing that line segment AD is equal to BC, we can safely say that triangle ADE is congruent to triangle BCF. This is because whenever two consecutive angles and a non-included side of one triangle are congruent to the corresponding angles and non-included side of another triangle, then the triangles are said to be congruent by the AAS criteria of congruence. Having proved both triangles congruent, we know that their areas are also equal to each other. In fact, we can now take one step further to add the area of the common region AFCD to both sides of this equation. The area of ADE plus AFCD is nothing but the area of parallelogram EFCD, while the area of BCF plus AFCD is the same as the area of parallelogram ABCD. In general, this shows that parallelograms that stand on the same base and lie between the same parallels are equal in area. Using this trick, King Laufey is sure to make his twins happy. For now, Jotunheim is safe from the twins' destructive quarreling. Fingers crossed, next year will go just as smoothly. Now that we've seen how two parallelograms sharing the same base and the same parallels have equal area, our next lesson will try to prove how a similar relationship also exists between two triangles. Tune in to find out how young Velma can apply this theorem to save herself from being eaten by her rogue pets.